Now we're going to talk about the intersection of two planes in space. Two planes intersect and generally they form a line. Of course, we can have two planes that don't intersect, which would be parallel, and two planes which are identical and they intersect everywhere. But we're going to consider the idea of planes just intersecting and creating this line of intersection. So one thing we know is that two planes are parallel if and only if their normals are parallel. So I'm using some symbols here, use those two bars, that's just the faster way of writing parallel. And when I say IFF, that's math jargon for if and only if. And if and only if is a biconditional statement, which means it goes in both directions. So if planes are parallel, then we know their normals are parallel. Or vice versa, if their normals are parallel, we can say that the planes are parallel. So a different way of saying this might be normal sub 1 is some scalar multiple of normal sub 2. So k being a scalar and n sub 1 and n sub 2 being vectors. All right, so they don't have to be the exact same vector. They can be scalar multiple normal vectors. But as long as those vectors are parallel, then we would know two planes are parallel. Now, if two planes are not parallel, then they intersect at a line, as you see in the picture. So these do not have parallel normals. They have different normals. Plane 2 has normal n sub 2, and plane 1 has normal n sub 1. So the line of intersection of these two planes is going to be perpendicular to both planes' normal vectors, n sub 1 and n sub 2. So what we're talking about when I say that is this line right here. Line of intersection I have just drawn is perpendicular to n sub 2, the normal vector to plane 2, and also perpendicular to n sub 1, the normal vector to plane 1. And I know they don't look like they're at right angles because we're considering this all in 3 space or R3. So reconsidering this, we can say that the line of intersection is parallel to the cross product of the normal vectors, or rather, the cross product of the normal vectors is a vector parallel to the plane's line of intersection. Now for our example, we're going to find a vector which is parallel to the line of intersection of these two planes. So as we just said, that line of intersection is going to occur if we cross product the normal vectors. So n sub 1 cross n sub 2 is going to equal the determinant of this matrix, I, j, k. N sub 1, we've got 3, negative 6, negative 2, and n sub 2, I have 2, 1, negative 2. And we've done a lot of these today, so I wrote my math out here. If you are unsure how to do that, you should pause the video and make sure that makes sense to you, or go back to a previous video and learn how to find the determinant of a 3-space matrix. And that's equal to 14i plus 2j plus 15k. So what we have here is a vector which is parallel to the line of intersection of those two original planes. Any non-zero scalar multiple would do as well. So I could scale this up, multiply it by 2 and get 28i plus 4j plus 30k. That would also be parallel. All right, so the scalar just means it's longer, but the vector still has the same direction. Let's do one more example. For this example, we're going to find the parametric equations for the line in which the planes intersect. So we have two planes written here. 3x minus 6y minus 2z equals 15, and 2x plus y minus 2z equals 5. Now these are the same two planes from the previous example. And in the previous example, we found a vector which was parallel to the line of intersection, as well as a point on the line. So our previous example, we identified that that vector parallel to the line of intersection is 14i plus 2j plus 15k. So this was the vector parallel to the line. So to find a point on the line, we need to take any point common to both planes. So we're going to find a point that exists on both planes simultaneously. And this can be found by setting any variable in both equations for the planes, setting any variable equal to a constant. And it's easy to pick one variable equal to 0. I'm going to say let z equal 0. So if I let z equal 0, that gives me 3x minus 6y equals 15, and 2x plus y equals 5. If I multiply this bottom one times 6, I've got 3x minus 6y equals 15. The bottom equation for this plane here becomes 12x plus 6y equals 30. Solving this system of linear equations, I've got 15x, the y's cancel, equals 45, or rather x equals 3. And if I know x equals 3, I can use either of my original equations. I'll pick 2x plus y equals 5. 2 times 3 plus y equals 5. I end up with 6 plus y equals 5, or y equals -1. So the point we're going to use, I found x was 3 when y is -1 and z is 0. So now that I have a point and I know that vector, and just to reiterate, v is equal to 14i plus 2j plus 15k. Now that I have that, I can write my parametric equations. So the line in parametrized form is going to be given by x equals 3 plus 14t, y equals -1 plus 2t, and z equals 15t. This is our solution. These are the parametric equations for the line which both of the planes intersect, that line of intersection. So remember, z equals 0 was an arbitrary choice. We could choose any easy value to deal with, and different choices are going to give us different parametrizations for the same line. So let's do one more example in this video. So for this example, we're going to find the point where the parametrized line intersects this given plane. Now, remember, this is the same plane that we talked about in the video prior to this. This was the plane passing through the points where z equals 1, x equals 2, and y equals 3. So it's this triangular plane here. X, Y, Z. We always use a right-hand coordinate system. So we know if we have an ordered pair, X, Y, Z, we can write that now as 8/3 plus 2t, comma, negative 2t, comma, 1 plus t. So this point is in the plane only if its coordinates satisfy the equation of the plane. So what that means is I can take each of these x, y, and z values and evaluate them in the plane to find what that parameter is to give us those points. So this gives me 3 times 8/3 plus 2t plus 2 times negative 2t plus 6 times 1 plus t. So I plugged each of those x, y, and z values into my plane. Solving this is going to give me a parameter t. So I have 8 plus 6t minus 4t plus 6 plus 6t equals 6. Combining like terms, I have 8t plus 14 on the left equals 6. Subtract the 14 from both sides. I've got 8t equals negative 8, or t equals negative 1. So at that parameter, t equals negative 1, that is where the point of intersection lies. So we're going to take that ordered pair up above, x, y, z, and I'm going to evaluate it for t equals negative 1. And so what that looks like is 8/3 plus 2 times negative 1, comma, negative 2 times negative 1, comma, 1 plus negative 1. That simplifies and gives me an ordered pair of 2/3, positive 2, and 0. So what this is telling me, this is the point of intersection where that line given to us in parametrized form intersects the plane. So this is a line passing through that triangular plane. So in this video, we talked about lines of the intersection of two planes, as well as a line intersecting a plane at a point in space.